Our next speaker is Jeff Groff, and the title of his presentation is Exploring the Relationship Between Antarctic Ozone Hole Size and Yearly Minimum Concentration. Thank you for that introduction, Dr. Groff. And as Dr. Groff said, the topic of my presentation is an exploration of the connection between ozone hole size and the yearly minimum ozone concentration over Antarctica. So stratospheric ozone, it's an important trace component of our upper atmosphere because it absorbs UV radiation, and UV radiation is harmful to life on Earth. NASA began monitoring ozone concentrations over the South Pole in 1979. This was in response to the depletion of the ozone over the South Pole due to the use of chlorofluorocarbons, hydrofluorocarbons, and hydrochlorofluorocarbons, which were used as propellants in aerosol cans and as refrigerants. These chemicals resulted in free chloride ions being introduced into the upper atmosphere, and these chloride ions catalyze a photochemical reaction that depletes ozone. And so NASA defined the ozone hole to be the region over the southern pole where the concentration was below 220 Dobson units. So here what I'm going to do is look at a data set that consists of the yearly maximum extent in millions of kilometers squared of this ozone hole size and the yearly minimum ozone concentration in Dobson units over Antarctica for the years 1979 through 2019. And the purpose is to determine if there's a correlation between these two data sets, between ozone hole size and minimum ozone concentration. So my null hypothesis is there is no correlation between ozone hole size and minimum ozone concentration. And the alternative hypothesis is that there is a correlation between ozone hole size and minimum ozone concentration. So in figure 1, I'm plotting these two data sets as a function of time. The green line shows ozone hole area in millions of kilometers squared each year from 1979 through 2019. And the magenta line shows minimum ozone, yearly minimum ozone hole concentration in Dobson units for each year from 79 to 2019. One thing to note is that in 1987, the Montreal Protocol was agreed upon, an international treaty to curtail the use of these chlorinated and fluorinated hydrocarbons that were depleting the ozone layer. And the protocol went into effect in 1989, which was the beginning of a reversal of the long-time trend of increasing ozone hole area and decreasing ozone concentrations. But it remains to see if there's a correlation between these two data sets. So in figure 2, I'm plotting ozone hole area as a function of minimum ozone concentration in Dobson units measured each year. So each blue dot is data point from each of these years from 79 through 2019. And a line of best fit is applied to these data points via linear regression, shown in the red line. And a correlation coefficient was calculated, and it revealed that there was a very strong negative correlation coefficient of negative 0.96 between these two dimensions of my data. And not only that, but a t-test was performed to see if this correlation was statistically significant. And the result of that test was that yes, this negative correlation is very strong and statistically significant, with a p-value much less than 0.001. So in the end, I reject my null hypothesis and accept my alternative hypothesis. There is a correlation between ozone hole size and minimum ozone concentration over Antarctica. So this data that I'm presenting here was collected by NASA, and it's freely available online to be downloaded. I provided the link down here where you can download this data and do your own analysis. And I'd just like to wrap up by saying special thanks to Dr. Stephen Payne for providing this link and also getting me started on this study to get me interested in this data set for analysis. So with that, I conclude my presentation, and I'll now open up to some questions.